This lecture video is going to focus on quadratic equations. So we're going to focus on how do we graph in vertex form, how do we graph in standard form, and then we're going to do some work with minimum and maximum values here. So let's go ahead and jump straight into it. So you should have a little bit of background about quadratic equations before stepping into this video here. So vertex form of our quadratic, we know that A, the number here in front, tells us if we're looking at a positive or a negative quadratic equation here. So we know if it's going to open up or open down based off the sign that we do have here in front of our equation. We also know if it has a compression or a stretch based off that value, and we'll deal with that here in a little bit. Otherwise, we're going to do quick sketches of quadratic equations in vertex form to start off with. So we're going to first look, does it open up or down? Let's find our vertex based off the equations. Again, remember, when we're given our equation in vertex form, HK right over here is the vertex for our function. We're also going to find the x and the y-intercepts. Keep in mind, to find any x-intercept, set your equation equal to 0 and solve. To find any y-intercept, plug in 0 into your function and solve that. So let's go ahead and focus on graphing this first example here. First thing we should be looking at is the front of the equation. This says a -2, which means we are looking at a negative quadratic equation. So as far as our graph is concerned, this should be turned downward, right? Open down is what we're looking at here, is what we know just by looking at the front of our equation. Regardless of the number, the negative tells us it's going to be turning down instead of up, right? If it were positive, it would look like this. Otherwise, the vertex of our equation is going to come from our equation. So inside the parentheses, this is our h. Outside the parentheses here at the end, that is our k, right? H is always on the inside next to x because the minus is part of the formula. So what you need to keep in mind, if you're pulling a number that comes from the inside of parentheses, you want to grab the same number, different sign. So just think the opposite of that number. In our case, h would not be a -3. We want a +3 for h. K is always going to be on the outside of your equation here towards the end. So for our particular example here, we have a +8. So that's exactly what it's going to be, a +8. You only need to change the sign if you're pulling a number from the inside of the parentheses. So I always think of it as opposite of the inside, same as the outside. So +3, +8. So that is going to be the vertex here. So I'm going to go ahead and start graphing this and piecing this together as I have this. So we have our vertex is 3, 8. So let's see, to the right 3, up 1, 2, 3, 4, 5, 6, 7, 8. So that is the vertex. And we do know our graph is going to be going downwards here, but we are going to focus on finding some specific points, mainly our x-intercepts and our y-intercept here. Now, let's start with finding the x-intercepts. In order to find the x-intercepts of any function, take your function, set it equal to 0, and solve it. Your solutions are going to be your x-intercepts here. So if we're solving this, first thing we're going to do is subtract that 8 to the other side, right? Drop the right-hand side down here. Go ahead and divide by that -2 there in front to cancel that out, leaving us with x minus 3 squared on the right-hand side and a +4 on the left. Take the square root of each side. Square root of 4 is a plus or -2. Don't forget about that. We get two different values there. On the right side, square root and square cancel, and we drop down the x minus 3. Add the 3 to the other side, and x is equal to 3 plus or -2. Keep in mind that represents two different solutions, 3 plus 2 and 3 minus 2. So our two solutions are a 5 and a 1. Go ahead and put those in on your graph. So a 5 would be here, the 1 would be right over here. So those are going to be my x-intercepts here. Now we just need to find the y-intercept. Find the y-intercept of any function, you want to plug in 0 and simplify it. When we plug in 0 here for x, well, let's see, that gives us negative 3 squared. Negative 3 times negative 3 is a 9. 9 times negative 2, that does gives us a negative 18. And negative 18 plus 8 is negative 18 plus 8 is a negative 10. So we are going to have a negative 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So our graph is going to look like we got our vertex from our equation, positive 3, positive 8. It's going to cut through that x-intercept of a 1, and it's going to keep going until it gets to that negative 10 is when it's finally going to intersect. And then the right side is just going to cut through that positive 5 that we found over here. This is what our graph would look like for that example. Moving on to our next example here, our graph is negative, so it is going to open down once again. Our vertex, again, think opposite of the inside, same as the outside. That's going to be a positive 1, positive 4. All right, so our vertex here, let me go ahead and start building that. So positive 1, positive 4 is where our graph is going to start here. It is negative, so it is going to be going downwards from here. So let's go ahead and find our x-intercept. Finding the x-intercept, set the equation equal to 0 and solve. So let's see, that's going to give us this. And let's solve this. Let's start by subtracting that 4 on each side, which is just going to give us negative 4 is equal to that right side. Divide out that negative there in front to give us a positive 4 now, and dropping down the x minus 1 squared. Taking the square root of each side, so we still get a plus or minus 2 on the left, and an x minus 1 on the right. Add 1 to each side, and x is equal to 1 plus or minus 2. Keep in mind, 1 plus 2 is a 3. 1 minus 2 is a negative 1. Those are our intercepts here. So we got an x-intercept at a positive 3, an x-intercept at a negative 1. I can go ahead and connect the right-hand side of my graph and go ahead and connect that through to its x-intercept. On the left, let's go ahead and find the y-intercept first. It looks like the y-intercept might be about 3, but let's go ahead and confirm that before we officially connect those dots there. Plugging in 0 into our equation here for our y-intercept. So let's see. That is going to give us a negative 1 on the inside of our parentheses. Negative 1 times negative 1 is a 1. Don't forget to drop down that negative from the outside, though, leaving us with the negative 1 plus 4, which is a 3, which means we do have a y-intercept of a positive 3. So we can go ahead and connect that left-hand side, and that is what our graph will look like. Our next two examples are going to be graphing quadratic equations when they come in their standard form here. So because they're in their standard form, we do not know the vertex of these equations, or not from the get-go, not from the equation. We can't just pull HK out of the equation. We're still going to look at the front of the equations if they're positive or negative, again, to know which direction they're opening up or down. Because these are not in their vertex form and we cannot easily find the vertex, we are now going to be using the vertex formula for that. Then we're still going to find the x-intercept and the y-intercept using the same process here. So let's go ahead and get started. Looking at the front of our equation, this is negative, so we know our graph will be going downwards. In order to find the vertex now, we are using the vertex formula. And that's going to start by finding negative b over 2a. That's going to be our x value. Whatever we get for our x value, we're going to plug it into x, right, as our f of x, and then we're going to get our y value from that. So find negative b over 2a. Whatever you get from that, plug it into your equation. That is your y value. Negative b over 2a, so keep in mind that comes from your quadratic equation. A is the coefficient of x squared, b is the coefficient of x. So in our example here, a is a negative 1 here, and then b is a negative 2. When we plug that into our equation, we get a negative, part of the formula, b is a negative 2, over 2 times a. Simplify that. Up top, double negative makes that a positive 2. Down bottom, that is a negative 2. And when we divide that, we get a -1. That is our x value for our vertex. So our vertex is -1 comma something. In order to find that something, take that -1 and plug it into your equation. Find f of -1. So that's going to look like -1 squared minus 2 times -1 plus 1. Again, just plug a -1 in for x into your equation here and simplify. Dropping down the negative, -1 times -1 is 1. -2 times -1 is a +2, and then plus 1. And when we add this up, we get a 2. That means our vertex is -1, 2. Let me go ahead and graph that. So far we know our vertex is a -1, 2, and it is negative, so it is going to be facing downwards here, which means we are going to have two x-intercepts. Our y-intercept looks like it's going to be somewhere between here, but let's go ahead and calculate that to be sure. Finding our x-intercept first, we are going to set our equation equal to 0 and solve, which is going to be just a little bit different than solving our previous examples. In solving our previous examples, we were essentially solving them using the square root property here. Taking a look at this form here, we are either going to solve these by factoring or we're going to solve them by throwing them into the quadratic formula. First, we don't want our leading term here to be negative, so let's divide everything by a -1 first, which is going to give us 0 is equal to x squared plus 2x minus 1. Now, this problem does not factor for us. It looks like it does. X times x to get x squared, 1 times 1 to get this 1 here, but we need our middle term to add up to a 2, and there's just no way we're going to get this to be a 2. In order to get that -1, one of these would have to be plus, one of these would have to be minus, right? Different signs give you negative. But if you take a +1, -1, you get a 0, and we have a 2 here. All right, so they need to multiply to get the last, add or subtract to get the middle. There's just no way we're going to be able to factor that, which means we need to throw this into the quadratic formula here. So plug that in, A, B, C. Quadratic formula is -b plus or minus the square root of b squared minus 4ac all over 2a. Calculating this real quickly here, we get a -2 up front, plus or minus. 2 squared is a 4. Minus 4 times 1 is just a 4. I'm sorry, that C is a -1. I just realized that I did write one of these down here. The C is a -1, so let's see. So this is going to be a -1 right over here. So this is a -4 times 1 times a -1, which is a +4 over 2. Bringing that over, -2 plus or minus the square root of 8 when we add those two together over 2. Square root of 8 is equal to 2 square roots of 2. But regardless, we're having to graph this. So at any point, you can throw this into the calculator in order to get those values there. When you throw this into the calculator, just keep an eye, -2 plus 2 square roots of 2 over 2, -2 minus 2 square roots of 2. You're going to get about a 0.4, which is going to be around here. And then you're going to get about a -2.4, which will be about there. Let's go ahead and verify on that y-intercept, though. So let's plug a 0 into our equation here. When we plug in a 0, that's going to be -0 squared minus 2 times 0 plus 1. The great thing about finding the y-intercept in this form is that anything has an x in it is going to disappear. Those are going to be zeros. So you're essentially just left with the number at the end. Our y-intercept is a 1. So that's going to be a 1 right over there, which I graphed it about correct there. And that is what our sketch of this would look like. Focusing on another example, this is also negative, so we know it's going to be opening downwards here. Let's go ahead and find our vertex, so -b over 2a. So, dividing everything by a negative first. Again, you never want your leading coefficient to be negative, so this is going to be f of x is equal to x squared minus 4x minus 1. A is a 1, B is a negative 4, C is a negative 1. So when we do negative b over 2a, that is a negative 4 over 2 times 1. Double negative up top makes that a 4 over 2, which is a 2, right? 4 divided by 2 is a 2. So our x value is a 2 here. Now find f of 2, which is going to give us, let's see, negative 2 squared plus 4 times 2 plus 1. So let's see, this is going to give us a negative 4 plus 8 plus 1, which is equal to a 5. I'm sorry, I don't know why I wrote a 2 there. All right, so that's going to be 2, 5 as our vertex. So positive 2, positive 5, going downwards here is about what our graph is going to look like. So just by knowing the sign and knowing the vertex, it really does tell us a lot about it. But to fine tune it and really know where it cuts through, we do need to find those x and y intercepts. Finding the x-intercept here. So let me go ahead and drop down our equation again. Here. So this is not going to factor for us either. There's no way 1 times 1 is going to add or subtract to give us a 4 here. So we are once again going to be using the quadratic formula. So let's see. Negative b plus or minus the square root of b squared minus 4ac all over 2a there. So you can throw that in your calculator, simplify it by hand. So let me see, 4 plus or minus the square root of, we have a 16 plus a 4 over a 2, giving us 4 plus or minus the square root of 20 over 2. So when we throw that in the calculator, 4 plus the square root of 20 over 2, 4 minus the square root of 20 over 2, we get a 4.2 and about a 0.2 there as our x-intercepts. So we can go ahead and do the right side here. Finding the left side, if we plug in zeros into our equation, we are actually left with a positive 1 there. So we can go ahead. Sorry, that is... Sorry, when we did our x-intercepts, that is a 4.2 and a negative 0.2. I'm so sorry about that. So that x-intercept is on this side. I was second guessing that, so thank goodness I caught that. So we have a 4.2 and a negative 0.2, so that makes sense where our graph cuts through the 1 and then that negative 0.2 there as the sketch for this one. Last thing in this section is dealing with a couple of questions dealing with the minimum and maximum values of quadratic functions here. So the formula to find the minimum and maximum value of a quadratic function is the same exact thing as finding the vertex of a quadratic. Because kind of think about that. If we have a negative parabola, its vertex is this right over here. And that vertex is the maximum point on the graph. If we have a positive quadratic equation here, its vertex is this. And that vertex is the minimum point on the graph. So the maximum, minimum point of a quadratic do come from the vertex formula, which are also the max-min formula. So if you want to answer the following question, find the maximum of this quadratic equation, well, just plug it into negative b over 2a. A is a 4, b is negative 16. So we have negative b over 2a, and simplify. That gives us 16 over 8, which is a 2 for our x value. Plug that in, find f of 2, which is just, well, let's see. Let's calculate this real quickly here. And 2 squared is 4. 4 times 4 is 16. So 16 minus 32 plus 8,000 here gives us 984, I believe, if I did my math correctly, which means the minimum point, actually, of this quadratic equation is a 2 in 984. So if you have a negative quadratic has a maximum point. If you have a positive quadratic has a minimum point. So this problem here, because it's positive, right, that means it's this form, This is actually a minimum point here, okay? So a negative has a max, minimum. A negative has a max, a positive has a min, right? So this represents a minimum point. Last example here, so maximization problem here with fencing. So let's read through this. It says a farmer has 2,000 feet of fencing in which to fence a rectangular plot of land. The plot lies against a river so that only 3 sides need to be fenced. What are the dimensions of the plot? What is the maximum area that can be enclosed? I always like to draw a little picture here. And if we draw a little picture, this is what we're looking at. So think of it this way. Our backyard is up against a river. And we want a rectangular plot of land that's going to be fenced in, that's pushed up right against that river. So we're only going to use 3 sides of fencing, and we're going to use the river as a natural border. We have 2,000 feet of fencing to do this with, so we want to figure out what is the biggest area that we can create based off of 2,000 feet of fencing. Now, it does want the dimensions. It wants the maximum area. And if it wants the maximum area, that means we are dealing with area of a rectangle. Formula for area of a rectangle is length times width. So this is our length, this is our width. Now, we need to try and plug in some type of information here. All we know is that there's 2,000 feet of fencing. And we can't solve this unless we try and figure out some information here. So we want to try and plug in to this formula here. We want to plug in something for the length or plug in something for the width. Now we have 2 unknowns. We need to find the length and the width. And if you have 2 unknowns, that pretty much makes it impossible to solve a problem with 2 unknowns. But if we just have 1 unknown, that's very doable. So in this instance here, what I'm going to do is I'm going to leave with the width. I'm not going to do anything weird or interesting with it. Width is just a width. We're going to call it W. I'm going to mess with the length here, and I am going to convert the length into something else here. So what I'm told is I have 2,000 feet of fencing, right? So if I have 2,000 feet of fencing, all right, and I'm going to put some for the width, some for the length. Now, it doesn't tell me how much I'm going to use. All I know is I have 2,000 feet of fencing. So think of it this way. If I have a pile of 2,000 feet and I need to separate it between length and width, I'm just going to take some from my big pile and I'm going to move it into a separate pile, right? So let's just say my big pile is going to end up being my length pile, right? But I need to create a width pile. Fencing I'm going to use for length, fencing I'm going to use for the width. I have 2,000 feet of fencing over here, and I'm going to move some of it to this pile. I don't know how much I'm moving it to that pile quite yet, but I know that I'm starting with 2,000 feet of fencing, and I'm going to take away, which means I'm going to subtract an amount for the width. Now, looking at my picture, do remember we have 2 widths. This is a width, this is a width. We only have 1 length, again, because the river is our border. So if I have 2,000 feet of fencing and I'm going to pull some fencing away for this width, some fencing away for this width. So it's going to look like this. 2,000 feet of fencing minus 2W. 2,000 feet minus this side, these 2 sides, is going to leave me left over what I'm going to use here. So the length is equal to 2,000 minus 2W. Little hint for these problems. When you set up these problems in the future, width is always going to be the width. The length is always going to be however much fencing they give you in the problem minus 2W every single time. And you're going to plug that into our little formula here. Length is 2,000 minus 2W. Width is width. Multiply this together. Multiply this. We get 2,000W minus 2W squared. Let me go ahead and switch this in proper form. Negative 2W squared plus 2,000W. All right, so it's in proper form. Notice this is a quadratic equation. And if we want to know the maximum area here, well, let's maximize this quadratic equation, which means if we are going to find the max, right, we are going to use the max formula, which is the same thing as the minimum formula, which means A is a negative 2. B is a 2,000, and let's plug that in. Negative 2,000 divided by 2 times negative 2. That gives us negative 2,000 over a negative 4, which is going to equal to 500. That represents our width. The width is 500 feet. And if the width is 500 feet, well, we can easily calculate the length, because we created a little mini formula here for the length. The length is equal to 2,000 minus 2w. Plug in 500 here and simplify this equation. 2 times 500 is 1,000, and 2,000 minus 1,000 is 1,000. So that means the length is 1,000 feet. The width is 500 feet. Those are the dimensions of our plot. Secondary question asks us to find the area. Now, area is length times width. So 500 times 1,000 is going to equal 500,000 square feet. This is a really, really big yard, a really, really big enclosed area here. 1,000 by 500 feet is going to give us 500 square feet here.